All right. So for section 7.1, that's Lagrange's equations for unconstrained motions. It starts off with a very general thing and then just moves into examples. So that's kind of what we're going to do here. The premises of this section is like, this is where it starts getting cool. This is where it starts getting interesting. And so basically the goal of what we want to do is find Lagrange's equations of motion. So we're like abandoning Newton's equations because we found something easier. That's what we're doing, and I'll show you how that's gonna work out for us. All right. So there's kind of our little goals there. And so the things that you want to know before going into this is you want to remember what kinetic energy is. That's 1/2 mv squared. And then I went through and broke it down into each component. Um, all the vectors after the v have a dot over it. It's kind of hard to see, but it's there. And then you want to know that the um, potential energy is dependent on the position of the object. So we don't really have an exact function of that because we don't know what its motion is like or where it is in the world. So we give it a general, just like, it's you. So then the book gives us just a definition for Lagrange's functions, and that's that basically the script L equals, so that's the Lagrange, equals the total kinetic energy minus the total potential energy. So this is just like a definition the book gives us. So we don't fully have a proof for that other than it works every single time. So it's kind of a proof in itself, but we're given it first. So that's the key equation for this entire thing right here, and the rest of it will just be more on how to use it and what it really means. So the one thing to note is that it's not the same as total energy, which is T plus U. That's not really the sign for total energy, so let me do better. Um, yeah. So we want to note that it's just not that. Later on in the chapter, it'll point that out explicitly and be like, and this is how we use both of them at once. So we don't want to get them confused. So the book, in kind of explaining this to us, it has us consider two different integrals or derivatives. So the first thing we want to consider is the derivative of the Lagrange itself with respect to x. And so what that'll do is, since the Lagrange is here, I'm gonna highlight them. Since the Lagrange, the only part of it that's reliant on x and x only is the total potential energy. That's basically all we get left with, is whatever that total potential energy is and its derivative of x. And since the total potential energy is negative, we have a negative. And what we know about the derivative of the potential energy, this seen in the last chapter a lot, is that its gradient is equal to the force. So the way that we're doing these derivatives is they're broken down into x, y, and z. So we're looking a bit more like these guys here. So when we look at the gradient, we don't really care that it's a gradient, we care that it's a derivative. So in other words, that right there is just equal to the force in the x direction on whatever that particle is. The next, oh no. So the next derivative it has us think about is the derivative of the Lagrange with respect to that dx, or so with respect to x dot. So when we do this, then we are only left with our kinetic energy portion. And when we take the derivative of that, we end up with just m dot. So that is what is the momentum in the x direction. But then if what we're getting really close to is actually just the Lagrange, the Euler-Lagrange equation that we've been dealing with. So I'm going to write that out here. Here we go. That wasn't it. We're doing this with respect to time. All right. So what happens next is in this equation, when I take this, what I end up doing is I get, basically I get m dot dot, which is the force, which is good because we really want it to equal this, and it does. So happy days, everything's good. That's basically how we really understand that it works out, but kind of like in backwards logic because it's a bit plainer to see that way. So what we can then do is say that this equation is true in all the directions, so all of x, y, and z. And we're just going to write that out. Just because the book really wanted to explicitly state it, it kind of backtracks over what was said in section 6.4, but the book really emphasizes that, so we're just going to really emphasize it with the book since we're just outlining the book. So the reason it's important to see this is that the Lagrange equation is dealing with each factor one at a time. So each dimension, this is why it works so kindly. You don't have to care about all the other dimensions while you're working with that one singular dimension. You can just focus in and basically zone out on everything else. And what gets really nice for that is when we get into constrained motion, which will be next section. But for now, we're going to stick with this oh no, come back. We're going to stick with this unconstrained motion. So that's what's worthy right there, worthy of being highlighted. And again, that's just exactly what was happening in 6.4. We just now have words for it. So this is the Euler-Lagrange equation, and then this is just the Lagrangian function. It's also called Lagrangian. So they're very close, but they're somewhat different, and they rely on each other. So what we also know from chapter 6 is that these three equations make it so that they satisfy like an action integral is what it called, of s equals t1 t2 l dt, and at this point that integral is stationary. And what that means is some dude claimed that, his name was Hamilton, and he was like, this is my principle. I forgot the L. So it doesn't really show us anything we didn't do in the previous chapter. We just now have its name. It's still noteworthy. It's one of the important equations in the chapter. And they're really proud of us for knowing that. But basically just know that these equations rely on this and this. Whoa, come back. These equations rely on this and that equation relies on that. So they're kind of a two-way street. Now, so I'm going to leave that up for a little bit and go through it. But the book wants to really provide us some statements of like what we've done so far. So in past chapters, the book went over how like Newton's second law can describe particles' path, so the equations of motion, which we did in class. And then what it's proven for in this chapter is that the three Lagrange equations, which were those blue ones that we just popped out, those also describe the motion. And if you want a more general of them, just basically replace x, y, and z with q1, q2, q3. And then the last one we did was Hamilton's principle, and we said that that also gives the equation of motion, just because it basically is the exact same thing as those three equations, since they rely so heavily on each other. So now what we're going to do is we're just sort of going to apply what we know, and we're going to do that first. We're going to start with, we're going to start with some Cartesian coordinates. So we're going to call this one particle in two-dimensional Cartesian coordinates. Definitely says 2 dimensions. Okay. So we're looking at this, and what we want to then do is it's very similar to what we just did, so that we know our Lagrange is going to be the Lagrange of x, y, x dot, y dot, and it's going to be equal to the total kinetic energy minus the total potential energy. And so we're just going to use what we saw before and write it down, but we don't have to bring z along with us this time. So what we end up getting is this right here. Oh, come back. Whoa. All right. Here, we'll make that slightly easier on us. All right. There we go. Okay. So looking at that, we're now able to just basically do the whole Euler-Lagrange thing of this guy. We're going to start with x, just because it's kind of nice, and we're going to do basically the same steps that we did above. So we know that the negative du dx is going to be equal to f of x, and we know that the derivative of the Lagrange with respect to x dot is going to be, I'm going to write it out, it's just going to depend on the kinetic energy with respect to x dot, which will just be m x dot, and that's going to be our total momentum in the x direction. So what we do from there is we're going to mentally just note that it'll be the exact same in y, and we're just sort of going to write it like that, kind of as more of one of our parameters functions, so that we can state that dl dx equals d or d dt of dl dx dot, and we're going to say that this can go back and forth between f of x, which through this one, if we take its time derivative, we know it's just mx dot dot. And then we do the exact same for y. And we just really honestly get the same thing. So what's the main point of this is that we can combine these two to just say F equals ma. That way we know it works exactly the same. We're gonna make those vectors. It works exactly the same as Newton's equations. It just got there without having to think about what it was doing. We just were like, yeah, so it moves and it has some potential. So it's going to do something like this, which is really nice to know. But where it gets really cool, also, sorry, one moment. One thing that it really likes to show is that the change in, so this delta t, so the change in momentum over time is equal to the force. So it basically just proves that theory while it's going at it, and in a different way that we see it, so that we see it still holds true with Newton's laws to every certain degree. All right. So the next thing it has us do is we're going to do the exact same thing, but in polar coordinates. So we're going to deal with one particle in 2 dimensions, but we're going to do it in polar coordinates this time. So how we're going to deal with that is we're going to do it quite simply the exact same way, but with a few slight differences. So we're going to take our Lagrange. Hey, come back. There we go. Our Lagrange. And we're going to note that this time the Lagrange is dependent on R and theta and R dot, theta dot. So it's still going to be that T minus U. And this time when we go in to write out what T is, we want to take into account that we're in polar coordinates. So this, first of all, the R dot is pretty simple. Just if R moves, it moves. But what's really interesting about what you have to do is that when it comes to theta, you have to multiply it by by R. So theta dot gets multiplied by R because your theta moving will only affect your motions and your particle with the R in total. And then they're both getting squared in this equation. So that's just an important thing to keep in mind. And then we do subtract that general function again, where we just note that there is potential energy. So we're going to break it into 2 parts, and we're going to do R and theta, and we're going to do them more separately and distinctly than we did with X and Y up at the top, just because there wasn't much of a difference between their derivatives, but now there is. So we're going to start with the derivative of the Lagrange with respect to X, and we're just honestly going to do the entire Euler-Lagrange equation at once. So what that ends up giving us is if we take it with respect, if we take the Lagrange with respect to R, we're left with this component and this component. So we get R theta dot squared minus whatever the derivative of U is with respect to R. And that's going to be equal to the time derivative of mass times that R dot. And what's nice about that is the time derivative of that is just mr dot dot. So what we can say about that is that this right here is going to be equal to just the force, like we saw a bit more up here. Go back up. So that negative du dx is just a force, and with the direction, so that's going to be the force in the r, like the component of the force that's proportional to the r of polar coordinates. So we can rewrite that just by putting everything else onto the other side and factoring out an m of everything. And this is the other side that we're talking about, these two sides. So we get r dot dot minus r theta dot squared. And that's what we end up with in sort of how the r is working out. So I'm going to draw a sketch of that because it's weird. So what that's basically saying is here's my graph, here's my r, and here's my theta. And then here's what I get produced as like a velocity. And it's going to be equal to r dot as a vector and plus r times theta dot as a vector. So it just sort of produces a different thing of like, this is how your radius will expand or contract, and it'll be, it's an interesting kind of thing to put in there, and it's weird to conceptualize, and that's why it's nice to have the Lagrange equation to help you deal with it. Now we're going to further look into the theta derivatives. So the derivative of Lagrange with respect to theta is going to be equal to the time derivative of the derivative of the Lagrange with respect to theta dot. So the derivative of the Lagrange with respect to theta, we're going to scroll back up to it so we can see what it is. That'll just leave us with part of the du r theta. So we don't have a theta elsewhere, so we're just kind of left with that, which we know will be a force. And then when we take its derivative with respect to theta dot, we'll end up with just that part. So let's go back down to where we're working. And we're going to go for it. So we end up with negative du d theta, and that's going to be equal to the time derivative of m r squared theta dot. Okay. So we're going to interpret this one side at a time. We're going to first interpret the left side, where we know that the force is equal to the negative gradient of u. And what we're going to write out there is that the gradient of u in polar coordinates, we have du dr r hat plus 1 over r du d theta, and theta's no happening. So what shows up differently here is that this is the gradient part of that function, of the function in polar coordinates, but we only have a part of it in it. So we can say that this right here is just the force times that r, so that the r is has disappeared and it doesn't need that anymore. So we're going to write that out here. Say R, F, and theta is what gets produced here. That way you don't have to see the R when it's in this form. But it's still going to be equal to that right side of the equation. So d dt m r squared theta dot. So then the book wants to direct us to the fact that this is something very familiar to us. It is angular momentum. So the sign for angular momentum is just a non-script L. And then the book also would like to point out that this is torque, which kind of just looks like a hangman. So what we get here is when we're looking at it, we can then read it as torque equals the change over time of the angular momentum, which is something we know to be true. So I'm just going to write that out clearly right now. Torque does have that right. It really does look like a hangman, guys. Is dl dt. And this is something we know to be true, so it still holds even in polar coordinates with the Lagrangian function. So from there, it's just nice to note that this works for any natural choice of theta is what the book explains, and that's just saying you don't do anything like, I don't know, so weird you end up in like a weird place. Just don't end up in weird places and this will work out for you, is basically what the book tells us. It's like, just choose something natural. Like, what's unnatural? And it's like, I couldn't tell you because I wouldn't choose it. And I was like, okay, that works for me. So just don't do weird things when you choose theta, and I guess you'll be fine. So what the book then wants to note is it has a section on several constrained particles, but it goes through the exact same derivation as 6.4. So I am not going to do that again. Instead, I'm just going to sort of give you the gist of it. So what it does is it does a derivation for n particles in 3D space. And what it ends up telling us is that there is going to be then a function that has an R1, an R2, R1 dot, R2 dot. I'm just going to sort of make my dot dot dots right there, so I only have to do one. And then Rn dot, because I did that in the right order. So basically that there can be an exceptional amount in there. That should be a capital N. I'm going to keep consistent. And what it then wants to point out is that since we're in 3Ds, there are 3 different ways it can move. And so that the fact that Lagrange equals T minus U, it's going to look, so I'm just going to write sort of the last equation only. It's going to look a lot like, oh, I should just write it all, shouldn't I? I'm going to write it as a sum, though. Equals 1 to n of 1/2 m r(I) squared. So that's what the total kinetic energy will look like. And then the total potential energy is a bit more arbitrary still. and it's going to look like that. So what it's then going to do is, since you're working in 3D, the number of equations it's going to produce is 3n. And that means it has 3 degrees of freedom and n particles. So it can move in all 3 dimensions in any which way it wants, and there are n number of particles to deal with. And that just sort of tells you how many Lagrangian functions you're going to end up with. And that's really all that is, and it's just 6.4 again. All right, so yeah, that's kind of just it for this chapter. It just sort of goes over something pretty brief. The next couple sections is where the Lagrangian functions step out there, and they're like, I'm ready for it, bud, let's go. And then they start getting like really cool. All right, so that's it.